the inverse of the product rule for differentiation. So here I have the product rule for derivatives, and u and v are functions of x, just like f or g. I don't know why they picked u and v, but they did. Integration by parts is also known as uv substitution because you're using u and v. So using the chain rule, or sorry, the product rule. The product rule, the derivative of two functions multiplied, is the first derivative times the second plus the second derivative times the first, second function times the derivative of the first. We do it the other way around, but it works the same way. Function times derivative of the other function times derivative of the first function. That's the product rule. That's what this is. If we take this and integrate, so we do the integral of the derivatives. Okay. The integral of the first one is just uv because it's the derivative of du. The second one is a function times the derivative. So we get the integral of that function times du, and then we get the integral of u dv. Rearrange this, and we get, and this is the important part here, the rest of it's just kind of how it's derived. So if you don't get everything else down, that's fine. This is your integration by parts formula. The integral of u dv is equal to uv minus the integral of v du. You start with an integral. This is what we're starting with. And we will end with a function and another integral. This formula, we use this formula of the product of two functions and no u du substitution properties. So you can't do a u du substitution. You can't do a regular u sub. That won't work. This is what we do. Okay. I'll make sure that's all the information. So I'm going to put the formula up here in a minute on the board off to the side because we'll want this in front of us the whole time. So the integral should have told you to bring colors. Colors are very helpful. Of u dv. And like I said, I'm writing it over here to the side just because we're going to want it in front of us the whole time. Equals u v minus the integral of v du. So we have a function and a derivative. We have to pick our u and our dv. This is what we're going to substitute. We're going to choose items in the original integral. This is our original integral. And we're going to choose our substitutions. We are going to pick, we get to pick something in there to be u. We pick something in there to be dv. And we take derivatives and antiderivatives of those two objects as necessary to come up with the other formula. The idea is you take something very complex, and you take that complex integral, and you break it down into a partial answer and a much simpler integral. That's the idea behind it. You take something you can't do, and you take it, and by breaking it into parts, you come up with a partial solution. That's the UV is a partial solution. And an integral we can do. That's the idea behind UV substitution. That's how that works. Everything in the original integral will be chosen to be either part of u or part of dv. Everything. Nothing from the original integral will not be substituted out. You will take everything that's there and break it up. It's either going to be in this party or that party. Nothing hanging out in between. Everything will be split. We pick u or dv. Everything in the original integral needs to be u or dv. Now, everything will constantly be in terms of x. We won't have u's and v's in there because u and v are functions. They're not objects. They're functions of x. Okay? And it's kind of, you need to see it. And I cannot underemphasize this statement right here. I cannot underemphasize that. You must be absolutely meticulous in your work. You must be organized. If you're not, you will be lost forever. Okay? It's one of those things. You have to stay organized. You have to be meticulous in your work. You cannot rush these problems at all. Okay? Now, the first and most important step is picking what your u is. What function, what portion of that integral is the u that you're picking, is that function. And Lipit helps you decide what your function is going to be. In this order, if you have a logarithm in your original function, that is your u. If you have a logarithm, that's your u. If you have an inverse trig function, that's your u. If you have a polynomial, that's your u. If you have an exponential, that's your u. If you have a trig, that's your last choice. If you have a combination of them, it comes in that order. If you have a polynomial and a logarithm, both, your u is the logarithmic function, and the dv is part of your polynomial, and the polynomial is part of your dv. It is in that order. Lipit good. Okay, and this is Lipit's. Oh man, when I saw this, I'm like, man, that helps so much. And this only works. Lipit only works for uv substitutions. But man, it really helps. Okay, logarithms, inverse trig functions, polynomials, exponentials, and trig functions. Generally speaking, I don't stick with inverse trig functions. I don't think any of the problems you have to do that. But you'll see a lot of logs and a lot of polynomials and some of the other ones as well. Okay. The idea is you let them be your u, because when you take the derivative of those objects, they get simplified. When you take the derivative of a logarithm, what happens to the logarithm? It goes away. The logarithm itself goes away. You no longer have to worry about integrating a logarithm if you let u be the logarithm. If you have an inverse trig function, you have the inverse tangent of x. The derivative of the inverse tangent of x is 1 over x squared plus 1. The inverse trig function is gone. You have some goofy polynomial to deal with instead, but the inverse trig function is gone. And if you take the derivative of a polynomial, all polynomials will eventually become 0 when you take derivatives. You may have to do it more than once, but they will become 0. They get simplified every single time. Exponentials and trigs don't, but those are kind of goofy if you have those in there. Okay? But that's kind of the idea behind them, is you want to eliminate it. You want to get rid of it if you can. So here we go. Notice I have in the notes right up on top, choose your u and your dv carefully. If you do not end up with a simpler integral, change them. Now remember, everything is either going to be u or dv. The x cosine x dx. Everything is going to be one of those. Everything is going to be one of those two things. There will not be anything in there that is unaccounted for. Now, like I said, choosing your u is the most difficult portion. And actually, let's stop and take a look at that function first off. You always want to ask yourself, can I do a straight up antiderivative? I can't. I've got x, I've got cosine being multiplied. They're being added, yeah, no problem, piece of cake, but they're being multiplied. I can't do that. I can't do u sub. If I let u be x, that doesn't help me. That gives me u cosine u, which is the same freaking thing. If I let u be cosine x, the derivative of then du would be negative sine x, and I have a sine in there, so a u sub isn't going to work. I don't have a choice in the matter. I can try other things, it isn't going to work. So I have to pick my u. Do I have a logarithm? No. Do I have an inverse trig function? No, thank God. Do I have a polynomial? What's my polynomial? X. X is my polynomial. I let u equal x. I have a polynomial. It is a polynomial. Okay. And so if x is my u, then my dv would be cosine x dx. Everything has been put into one or the other. That's my first and most important step. Everything there is one or the other object. Okay. So I have my u du. What's the derivative of x? Dx. Okay, and with dv, I start with dv, so I go from dv to v. That means I do what to cosine x dx? I do the antiderivative. The antiderivative of the cosine is the sine. Don't worry about plus c till your final answer. Yes.
Why is cosine x dx dv and not v?
It's the way the formula is. Remember, your original function, this is the formula here. The integral of u dv. So I have to take my original function, divide it up into a function, and the derivative portion of, or the dx portion of my function. So I will always have, if nothing else with dv, I will have dx, but I will have something else dx. And the idea is that will kind of go away. So I'll be doing antiderivatives and derivatives both when I'm setting this up. Now it's strictly writing out the formula. So my original problem, the integral of x cosine x dx equals, and then I do, and it's what? It's uv. So this is my u, this is my dv here. So it's uv, so it's x sine x minus the integral of v du, which is sine x dx. I had taken a complex integral, x cosine x, come up with a partial solution, and a very easy integral to do. The integral of negative sine dx. That's easy. That's this is a what? The integral of the sine of x. That's a walk in the park. All I have to do is take the antiderivative of the sine. That's easy to do, right? So my final answer is x sine x plus cosine x plus c. Because the antiderivative of the sine is negative. Antiderivative of the sine is negative cosine, but already negative there. So once again, the idea is you take this complex, difficult to do integral, and you come up with a partial answer and something easy. Why did I pick the polynomial? Because it freaking went away. It's gone. This function disappears. Trig functions will never disappear. Sines and cosines, they will never go away completely. But if I get rid of the polynomial, then I've got something easy to work with. That's the idea. That's the beauty of this whole thing. Take something nasty, come up with a partial answer, and something easy. That's the idea behind it. Come on, there we go. It's supposed to keep. Come on. Come on. There we go. Okay. Example number 2. Go ahead. Pick your U, pick your dV, come up with du, come up with v. Remember, lipid. They all wear radiation suits and flower pots on their heads. You also like this because I get to think of Devo all afternoon now. Okay, what's your U? Logarithms. It's the L. Let it be the logarithm. So then your dV would be t squared. Okay. So what's your V? If dV is t squared, your V is 1/3 t cubed. And I forgot t squared dt. And if u is the natural log, du would be 1/t dt. And now I can do this. And you're like, but it doesn't look much simpler. I mean, God, the derivative, I got a 1/t part of my dt in there. Well, if you stop and look at it, it is now uv. And so v is 1/3 t cubed, and then u is natural log. So even though it's uv, I always put the natural logs last. So I have 1/3 t cubed natural log of t minus the integral of v du. 1/3 t cubed times 1/t dt. Looks nasty. I mean, you're thinking, oh my God, I got 1/t. I'm going to have to take the derivative or antiderivative of that. It's going to really screw me up. Look what happens to it. You end up with 1/3 t cubed natural log of t minus the integral of 1/3 t squared dt. That's easy, isn't it? Relatively speaking, right? I mean, think about it. It's now a very simple polynomial to do. So I end up with 1/3 t cubed natural log of t minus 1/9 t cubed plus c. Yeah, your logarithm is disappearing. If you have a logarithm with a polynomial, it's done. Okay. The hardest part, I do honestly believe, the most difficult part of this one is choosing your U and then your DV to follow. But if you follow limit for your U, it really does make it simpler from there. That's what you've got to do. You've got to follow limit. Once you follow that, pick your U, then your D, then whatever's left after you choose your U, make everything else your DV, go from there. Okay. Okay. We've seen this before. We've actually seen this done. You've seen this done in film. Remember when we watched, what was that movie we watched?
The one with the Hispanic dude?
Yeah. Stand and Deliver. He talks about this method in here. He calls it the tic-tac-toe method, which really doesn't fit as far as I'm concerned, but the name is stuck, and a lot of teachers call it that because of the movie. I know the movie's like ages compared to you guys. I mean, it's older than you are by a lot. Doesn't mean it's bad. It's a little dated. But that's what this method is. It is UV. It is UV kind of tweaked a little bit. And it's actually an easier way of doing UV, but certain conditions need to be done. One of the functions has to be a polynomial. In fact, your U function has to be the polynomial, where dv would be the other part. If you have a function that's a polynomial, if that's what your U is a polynomial, you can do this method. And rather than doing it as a U and dv, you just come up with two functions you're doing, f and g. Okay, and you divide it up into the polynomial and the other function. And then you set up a table, and we'll set up the table here in a minute. And the table will have repeated derivatives of f and repeated antiderivatives of g. So you take the derivative, take the next derivative, take the next derivative until that disappears. And then you do corresponding antiderivatives. And using those derivatives and antiderivatives to come up with your solution. But which is basically doing UV substitution over and over and over and over and over again. Because what happens with the polynomial, if you go to UV substitution and you let U be the polynomial, it gets simplified. Now, so far, it's the first one we did, the polynomial is x. What happens if you take the derivative of x? It disappears. But if you have something like x cubed plus 2x squared minus 3x minus 5, it doesn't disappear right away, but it will eventually. And what will happen is if you have a complex, if you have a polynomial, third or fourth degree polynomial, and let's say your dv is the sine or cosine, then what you're going to do is you're going to do this, and you're going to do a uv for that again. And then you're going to have the same thing over and over and over again until that polynomial disappears. Tabular integration organizes that work. Rather than doing this over and over and over again, you do it in a table instead. That's what tabular integration does. It takes this that ends up being repeated because your U is still complicated. It's simpler, but it's still too complicated to do, to where where this part of the UV substitution needs another UV substitution, and then another UV substitution of that until eventually it disappears. That's what tabular integration takes care of. So let's do an example here. Use tabular integration, and the use alternating signs. You'll see what that does here in a minute. So I can't move the table up. That's okay. So what I need to do is I need to take those two functions, divide them up into my f function and my g function. My f function is my polynomial. So my f function is x cubed. The other function that's left, e to the negative 3x. We're going to pause first. Okay, So here's what you do. You take your integral, divide it up into f and g, the two functions. And then you have your table and you take the derivatives of f until it goes away. So I start with x cubed, 3x squared, 6x, 6, and then nada. And then I have to do the opposite with my g function. I do antiderivatives. I integrate. So I take the antiderivative of e to the 3x, or e to the negative 3x. Well, that would be negative 1/3 e to the negative 3x. You see where the negative 1/3 e to the negative 3x came from. Because when I take the derivative of e to some function, it's e to that function times the derivative of that function, right? So the derivative of e to the negative 3x would be e to the negative 3x times negative 3. I don't have a negative 3 up here on top, so I have to have a negative 1/3 to get rid of it. It's really nice. All this does will alternate signs, and my denominator will increase by a power of 3 each step. So this one actually is pretty easy to do repeated antiderivatives of. So I end up with 1/9 e to the negative 3x, negative 1/27 e to the negative 3x, and 1/81 e to the negative 3x. And I just have to do as many as I have until I get down to 0. And I have everything I need to do my solution. What I do is each term of my answer is the product of these two diagonal items. So my first term is negative 1/3 x cubed e to the negative 3x. That's my first term. Okay. My second term, I do the same thing with the next two items in each column. But here's the deal. My first one is a positive version of those two. My second one is the opposite of those two multiplied. So it goes what they are. It'll go plus this, minus the next one, plus this, minus the next one, plus this, minus the next one. So I have a minus whatever those two things are. 3x squared times 1/9 e to the negative 3x. The 3 times the 1/9 gives me 1/3 x squared e to the negative 3x. Same thing. 6x times negative 1/27 e to the negative 3x. And it would be plus that, plus minus, plus minus, plus minus, plus minus. So it's easy to remember that. The first one is the same, the second one's a minus, plus minus. So it's plus this, minus whatever those two things are, plus whatever these two things are multiplied together. So 6 times 1/27 is 2/9. So it'll be minus 2/9 x e to the negative 3x. And then one more, multiply those two, and it's minus whatever they are. So it's minus 6 times 1/81 e to the negative 3x. 6 over 1/81 is 2/27. 2/27 e to the negative 3x plus c on the end. If you didn't do tabular integration, you would get uv. This would be your uv, and then you'd have an integral. This would be the uv of the next integration by parts, and you'd have an integral. This would be the next uv from the integration by parts, and then you'd be able to do that one. So you'd have to do, like, I think it's 3 uv substitutions before you're done. This lets you do repeated uv substitutions without actually doing repeated uv substitutions. It only works under one condition. Your u is a polynomial. If your u is a polynomial, this is what you do until it disappears. Now, if my u is something like x squared, let me not do this. X cubed or higher, you bet your butt I'm doing this. But you see this is the tic-tac-toe method that he was talking about. Okay. Pick your u and your v. Your u and your dv. Follow Lippitt, pick your u and your dv. First step actually isn't too bad. If you follow the rules, do I have any logarithms? Do I have any inverse trig functions? Do I have any polynomials? Do I have any exponentials? So that means u is e to the x. So du is e to the x. dv would be cosine x dx, which means v is sine x. So let's rewrite this. So I get the integral of e to the x cosine x dx equals uv e to the x sine x minus the integral of v du e to the x sine x dx. And I can hear many of you going, because I have this strong mental power, I can hear many of you whimpering and trying. Mr. Horace, I thought you said they'd get simpler and easier. That's pretty much the same freaking thing we started with. E to the x sine x is nearly e to the x cosine x. It's not. It's close. Again, take the integral that's there, e to the x cosine x, do a uv substitution for that. Again, trust me, I know what I speak of. Do another uv substitution on the second integral. Remember, the beginning part will not change.
Wait, UV or?
Do a uv substitution on the last integral. So you will still have the integral of e to the x cosine x dx, which is what we started, equal to e to the x sine x minus some uv substitution.
What's the table one called?
Tabular.
Tabular. What?
Tabular integration. And actually, you've already done half of the uv substitution, right? Because you can still use the same u, because the u is still the same, e to the x. The only thing that's changed on this one, on the second time around, you still have u is e to the x, so du is e to the x. Now you have dv is equal to the sine of x dx, so v is equal to negative cosine x, negative cosine x. So I get minus, do my u's and v's for the second one, uv minus cosine minus e to the x cosine x minus the integral of v du minus e to the x cosine x dx. get rid of the brackets, distribute the negatives, combine up all that stuff. So I now have the integral of e to the x cosine x dx equals e to the x sine x. Those two make a positive. Take the negative, distribute, that becomes positive, that becomes minus again. So I get plus e to the x cosine x minus the integral e to the x cosine x dx. And you're probably too young, but you might remember this is the integral that never ends. Because if you were to do it again, what would you get? You just got what we started with. Maybe do it again, maybe again, and again. This is the integral that never ends. Except, nope. Algebra. Add the integral of e to the x cosine x dx to both sides. You can add or subtract anything you want to an equation as long as you add it to both sides. You can divide anything you want as long as you do it to both sides. Right? Basic algebra. You can do anything you want as long as you do it to both sides. So on this side, I no longer have the integral of e to the x cosine x. I now have 2 e to the x cosine x dx is equal to e to the x sine x plus e to the x cosine x. And I'm going to go ahead and throw my plus c in there because I have an integral on one side and no integral on the other side.
It's not on.
But I don't have my original problem that I started with, do I? I have 2 of them. How do I get rid of the 2 in front? Divide everything by 2. So my final answer would be the integral of e to the x cosine x dx is equal to 1/2 e to the x sine x plus 1/2 e to the x cosine x plus c. And yes, this happens. But I've solved the problem, haven't I? I've integrated e to the x cosine x. I have the integral equal to a non-integral. I can now evaluate, I can do whatever I want to. But I've integrated the function now. Yeah, I've given you all the examples, basic examples there are of UV substitution. One of these things happens. Either everything disappears and you get something nice and simple, and the second one is easy to go. Or you have to do repeated ones because you have a polynomial that has to go away after a while. Or you get this where what you started with, you get back. These are your possibilities. Yes, question.
How come C is being divided by 2?
What is a constant we don't know divided by 2? A constant we still don't know.
But if we you're plugging in to find I forgot what
it doesn't matter. It wouldn't matter anyways. It wouldn't matter at this point. If I'm plugging in to figure out what C is, and if I'm evaluating what plus C is, then there is this. If I have bounds, if I have bounds, you don't have to worry about the plus C. You have to evaluate. If you have bounds, integrate completely, get to this point, get to the point where you have the integral on one side and the non-integral on the other side, no partial and not partial. Wait till it's completely done and then evaluate. Do not plug in the bounds until you've completely eliminated the integrals on the other side. So don't do, go halfway through, and I'm going to take these bounds, put them over here, and I'm going to evaluate the first part. Don't bother. Just do the integral, and then evaluate your antiderivative when you're done. Okay, not too many of the problems have bounds on them, but they will have bounds on them from time to time. I don't believe I use bounds on the test because it's just too cool. At least not on UV subs. So there's a hand possibly. Possibly. But if you see bounds, probably not a UV sub. But I just don't do a lot of balance on this test anyways. So. Are there any questions? Because this is yeah. I like UV subs. I do. I like them. I know you're rolling your eyes and going, God, you're nuts. But it works. And I know that, like I said, this is not going to be part of the AP test, so technically it's not something that I need to cover in here, but I do it anyways because this is the best time to introduce because it ties in with everything else we've done. It makes sense to have it here. The other methods of integration, I mentioned a couple of them, integration, trig substitutions, and partial fractions. They don't fit with anything else that we're doing. They can be a standalone that you can do later. I don't want to throw them into the mix. This really fits with doing the U subs and the other stuff. They all kind of tie in together. And I think that this is difficult enough, at least introducing it now in a relatively simple form, is better than having you do it next year. Your Calc 2 is actually probably the most difficult semester of calculus. I do believe I'm done with this, right? Yeah. Yep. I